Okay, so let's kind of recap where we are so far. Right now, we have figured out, hey, there's an equation for the force between two charged particles called the electrostatic force, and that's K times one charge times another charge divided by R squared. Okay, and we know that's this is a force, so it's a vector, and it's got a direction, all that kind of stuff. And this is very similar to the force of gravity equation that was big G times mass 1 times mass 2 divided by R squared. All right. Then we just learned something about something called an electric field. That was K times 1Q divided by R squared. And we've kind of sort of discussed how there's something very similar to the electric field in gravity, and we had calculated it before as being big G times mass divided by R squared, and that was the gravitational acceleration. Remember that the electric field basically tells us how much force per coulomb, so this is kind of a unit of coulomb, how much force there is per a unit of coulomb in the electric field of another charge. So say we have a positive charge here, we saw that the electric field radiates out in all directions from a positive charge. And let's just say, okay, at this point right there, what would be the electric field? Well, we would use this to calculate that, and it would be able to tell us, okay, well, if I put a 1 coulomb charge there, this is how much force we would have. So there's something similar to that going on in gravity, but we didn't really discuss it in all that in great detail when we went through this when we first got to gravity. Okay, so there's one more piece of information that we need to talk about with regards to electrostatics and how it might actually extend to gravity. There was one thing that we talked about with gravity, and it was about energy. We talked about gravitational potential energy. So the potential energy, that's not a P. All right, so the potential energy for gravity's sake was the equation mass times gravity times height. You could also rearrange it as being the force of gravity times the distance that you lifted something. So this is a force times a height. So this is saying if you have an object of mass m and it's above the ground, a height h, then this is how much gravitational potential energy is there, m times g times h. You could also look at it as being a force times a distance, so it's kind of like the amount of work you had to do to lift this object up. Now, this is kind of like a change in energy, right? We usually set the potential energy down here to be equal to 0, and we are measuring the potential energy with regards to that 0 point down here. So it's force times gravity times height. Well, if we take a look at how that relates to the electrostatic force, the electric field, and all that kind of stuff, we've already drawn way, well, we've drawn a lot of parallels in between gravity versus electrostatics. So can we do the same thing here? And it turns out that we can. Okay, if we talk about work as being a force times a distance, then the force equation is K times Q1 times Q2 divided by R squared. And again, we're using distance as R here. So if we take that and we multiply it by an R, then we get the equation for work, or the potential energy for electrostatics would be K times Q time Q1 times Q2 divided by R. Okay, K times Q1 times Q2 divided by R. So this equation is very similar to the equations that we've already seen up here, but it's got two charges and only one R. The unit for this would actually be in joules. It would be joules. And we can take a look at how that would happen. K has a unit of newtons meters squared per coulomb squared. We're going to multiply that by two charges that are coulombs. So we got a coulomb squared there that's going to cancel out. And we divide it by a meter, so only one of the meters cancels out. And we're left with a newton meter. And we've already seen this before. It is the same thing as a joule. It's force times distance. So we have a new equation here that talks about work. Well, what is this actually talking about? What work are we doing? Well, everything with electrostatics is talking about you have one charge here, and I just made it positive. Doesn't have to be positive, it could be negative. And there's an electric field that is coming out in all directions. Okay, so we have a charge here. Now, how much work would it be, or would it take to bring another charge, call it another positive charge, and put it right here? Now, we know that if we are trying to put a positive charge near another positive charge, then there's going to be a force on it. There's going to be a repelling force that's going to try to push it the other way. So we have to exert some amount of force to put this charge here. We have to do work in order to make this configuration. And the amount of work that we would have to do would be the same thing as the electric potential energy. It's sometimes written as EPE or PE with the subscript E. And let me just be consistent here. So the electrostatic potential energy, the electric potential energy, as being K times Q1 times Q2 divided by the distance between them. And that's how much energy is basically put into the system, how much energy you have in this configuration. If you were to let it go, they would fly away, and this is how much energy, this is how much work you had to put into it. That's how much energy you would get out if you were to let it go. So let's do a quick calculation. If I said that this is 5 nanocoulombs and this one is 6 nanocoulombs, they're both positive, then we can do this calculation. The amount of potential energy or the amount of work that you have to do is equal to K, which is 9 times 10 to the ninth, and it is newtons meters squared per coulomb squared multiplied by 5. Now, what is nano? Nano is times 10 to the negative ninth, and then we have 6 times 10 to the negative ninth. Now, this is very similar in centimeters, millimeters, whatever it is that we're dealing with. We don't work in nanocoulombs. We work in actual coulombs. So we have to put this back into coulombs. And so what we have is 5 times 10 to the negative ninth and 6 times 10 to the negative ninth over the distance between them. Let's say the distance between them is 1 centimeter. So this would be divided by 0.01. Okay. We can do the calculation, and I'm going to kind of do this in my head if I can. 5 times 6 is 30. 30 times 9 is 270, so that's 270. We have a times 10 to the ninth multiplied by a times 10 to the negative ninth, and those would cancel out, right? It'd be times 10 to the 0, which gives us 1. And we're left over with another times 10 to the negative ninth, and we are left over, or put this over 1 times 10 to the negative 2. Okay, and we know that exponents, we can say that this is 270 times 10 to, what is that, negative 7 joules. Okay, we can make it look even prettier. We can say it's 2.7 times 10 to the negative fifth joules, if you want to put it in actual scientific notation. So this is how much energy, how much electric potential energy is right here in this configuration. Now, if you recall when we talked about gravity, we had this energy measured from some 0 point. Well, the 0 point is off at infinity. And we're saying that we are bringing this in from infinity, and the electric potential energy, the potential energy for the electrostatics, is equal to 0 at infinity, just really, really far away. Okay? So that's our reference point. We're bringing it in from really far away, and this is how much work we had to do to bring this in. So yeah, if we did this with, say, a negative charge, we have a negative charge, say an electron, and we know that the electric field for the electron is going towards, that's not what I wanted to do, different color. We know it's going towards the electron in all directions, radially speaking. How would that change this whole situation? Well, if I still wanted to bring in a positive charge, that doesn't change. I'm still going to bring in a positive charge. Am I going to have to force this positive charge into the electron or get it near the electron? Well, the answer is no. A positive charge wants to be near an electron. So we actually have to do what we would consider negative work. The electric field, the electron is the one pulling the proton, or the not the proton, but the positive charge close to it. So we don't have to do any work. The electron itself is doing the work here. So if we did that calculation, it'd be K times Q1 times Q2 divided by R squared. Q1 would be negative, Q2 would be positive. We would end up with a negative amount of energy. Well, if you remember, energy is a scalar. We really can't do negative energy, but we kind of sort of talked about this in thermodynamics. If this is the amount of work, we're really talking about work that someone else does. We don't do this work. It's negative work, and it's the amount of work that something else does. In this case, it'd be the amount of work that the electron does. So this is everything about the electric potential energy, electric, if I can spell it, electric potential energy, and how it relates to the gravitational potential energy.